A good example of a capacitive sensor is a condenser microphone. A condenser microphone takes audio signals, which is essentially air pressure variations, and converts it into a voltage output. A condenser microphone essentially consists of a pair of conducting plates, as shown here. One of these plates is stationary and it is fixed to the casing, while the other plate is fixed through a spring to the casing. And as sound falls on this plate moves back and forth, and that changes the distance between the two plates and therefore changes the capacitance of this sensor. And this capacitance is converted into the voltage by the circuit here. So let's see how this works. The equivalent circuit of a condenser microphone is shown here. So we have a capacitor which changes in response to sound, and we have a voltage supply and a resistance attached. The output is the output voltage across the resistance is picked up and amplified further. Let's just take a closer look at the condenser microphone. So the capacitance is given by this equation, as we have already seen. Now the charge on the capacitor is going to therefore be given by C into V, where V is the voltage on the capacitor, and therefore the charge is going to be given by this equation. Now this equation is non-linear in L. Now we want to make it linear in L because L is the quantity that is changing in the capacitor, and that is the capacitance is changing as a response to the change in distance between the two plates. So one way of linearizing this equation would be using a Taylor series approximation, and the first two terms for a Taylor series approximation are given in this equation here. So if you write Q naught is basically Q, which is the charge on the capacitor, and essentially we write that equation for the stationary position or for the starting position, and in that case the distance between the plates of the capacitor is T. So instead of L we have T, and the voltage across the capacitor is going to be just the voltage of the source, which is E. Similarly, if we differentiate Q with respect to L and Q with respect to V and substitute values in both these equations, we get these terms. And in this case, we can see that we have linearized the equation with respect to L, and instead of L we are using X as the displacement. So we have a relationship between the charge on the capacitor and the displacement X. Okay, so charge is not a very good quantity because we cannot measure it. So let's just look at what happens when you write current. So for getting current, we differentiate Q with respect to T. Now this is a constant term, so this disappears. And if you differentiate this, we get dx over dt, and the rest of the term remains the same. And if you differentiate this term, we get this. And the basic reason why we get this is because delta V can be written as I into R, because the change in voltage is also the voltage that appears across the resistance. And this gives us a differential equation which relates a current and the displacement of the capacitive plate of the condenser microphone. We can take that differential equation that we got in the previous case, which is here, and we can convert it into the frequency domain. So you have I omega, and essentially all the terms remain same except dx by dt is replaced by j omega x omega, and di by dt is replaced by j omega I omega. If we do some algebra, and we will get the transfer function which is given like this. So this is a relationship between the current that is induced in the circuit as a response to the displacement of the capacitive plates. Now from this we can get the output, what the output voltage across the resistor is going to be. And that's basically going to be done by multiplying I over X with R, because R into I is the voltage or output of the condenser microphone. And if we do that, we see that the output of your microphone and the displacement are related by this equation. Now, what is interesting here is that this is a relationship, this is a gain relationship. It tells you what is the gain, how does a displacement result in what voltage of the condenser microphone, and it tells that with respect to frequency. So let's say if omega is 0, that is it's 0 frequency, or you have DC pressure applied on the condenser microphone, what is the output of the condenser microphone going to be? It's going to be essentially 0. So for DC, you're going to have a 0 output. What about very, very high frequencies? So let's say high frequencies. So for high frequencies, what is going to happen is this term is going to become much larger than 1, and therefore j omega tau and j omega tau cancel together, and you have a constant gain of E over D. Okay, and what happens at medium frequencies? The gain is going to increase and become E over D. So the gain frequency curve, if you plot that, omega versus Vc over X, is going to look something like this. And therefore this has something like a high pass characteristic. Of course, what we have not really looked at in the condenser microphone is the mechanical construction of the condenser microphone, because one of the plates is attached with springs to the casing of the condenser microphone, and that is also going to result in some changed dynamics of the system.